All right, hello everybody. Welcome to Monday evening of our second week of the module. So hopefully you had a chance to review the lesson from Friday on polymers. Sorry, you know how the days sort of run together and you just can't remember which day is which. So that was polymers. I'd be happy to take your questions if there were things that weren't clear that you don't understand from that. Today I'm going to focus on acids and bases to get you ready to complete the lab. So just one note about the lab before we actually go into the chemistry behind it. So this is kind of a mixed virtual versus in person. We didn't know until kind of the last minute what we would have, and I know some of you are out of the country or weren't able to get a lab kit, so we're going to keep that kind of hybrid setup. So pretty much everything you need on this lab is right here in the document, all the pictures, and you write your observations, kind of like the chemical reactions lab we did a few weeks ago. So, pretend you're doing this in the lab and you write down the observations that you see on the document as though you were watching it in the actual laboratory. What's a little bit different about this one is to try this at home. So if you want to do some more stuff, you can. In your take-home lab kit, there's a little tea bag, and that is an indicator, an acid-base indicator. So soaking that, or putting that tea bag in water will turn that water into an indicator solution that you should then be able to use to measure acidity and basicity, which you can then test with various household items. You can do these other ones too. Some of you have already done these for your at-home experiments. If you've already done this, you can put in your pictures and data from your at-home experiments. That's fine. You don't have to do it again. But if you want to check out the indicator T, definitely give that one a try. And then, as usual, which I know I've commented on some of your at-home experiments dealing with acids and bases, when you're testing household materials, the only real danger is that remember that those household materials can be in themselves hazardous. So just because something is in your house and you bought it at the grocery store in a bottle does not mean that you can treat it like it's water. And this is particularly true with cleaning chemicals. So things like powders like Barkeeper's Friend or Comet can be really, really bad if you get them in you. Drain cleaners are pretty reactive, are usually really, really strong bases. And toilet bowl cleaners are strong acids. Sorry for just giving all these away, but I don't really want you to test those kinds of things because outside of their intended purpose, you don't want to be messing around with a whole thing full of a drain cleaner that could get spilled and knocked over on your kitchen or something. All that stuff can be really corrosive, and it can also cause big problems if you mix it together. So if you have any cleaners with bleach in them, make sure that those never touch acid, because acid and bleach together can release HCl gas, which can be really, really bad to breathe in. So if you have a bleach-based bathroom cleaner and you're using that, and then you've got an acid-based toilet bowl cleaner, and those were to mix, you could be producing some pretty dangerous chemicals. Same thing with ammonia and bleach. Ammonia is in glass cleaner, like the blue, Windex, that kind of stuff. And if that mixes with bleach, you can make chloramines, which are also toxic compounds. And if you're in a bathroom, for example, a fairly small room, and it's not well ventilated, you're making these gases, and you could be really hurting yourself in there. So you got to be careful with those home chemicals, cleaning chemicals, even though you can just buy them. You don't need to be, you don't need some special chemical license to have those things. They can still be really hazardous. So if you do an experiment like this and you're testing household items, it would make me feel a lot better if you stick to things like foods and things that aren't going, that soaps, shampoos, things you use on your bodies, lotions, those kinds of things, rather than those more corrosive surface cleaning type chemicals. And certainly don't go out in the garage and grab a bunch of weird cans of solvents from the hardware store, because then you're also mixing in organic solvents that have their own issues. So that's just my little plea for some safety, and hopefully you can finish this stuff out pretty safely. All right. So let's take a look at some of the chemistry of acids and bases. All the stuff I'm going to say tonight is also in, much of it is in the lab, in that first part of the lab, and then it's also in the reference documents that I've linked. But I know that when you just like read a chapter or something, it's sometimes hard to tell what's really important, what you really need to know out of that. So this will serve more like an outline or a guide through that material. As usual, if you have questions, post them in the chat or on Discord, and I'll try to answer them right away. All right, so first thing about acids and bases is we have to define them. Like, what are they? What's an acid and what's a base? And that ends up not actually being such an easy question. There are different ways of defining acids and bases, and the way that we're going to define them is something called the Bronsted-Lowry definition. And it looks like this. Acids are molecules that give up hydrogen ions, H+. And we're going to talk about what these things mean. And then bases are molecules that accept H+. All right, so acids give up H+, bases accept H+. So what does that mean? Well, let's take a look at a reaction and see if we can see what's happening in this reaction. All right, so we're going to look at the reaction of HCl and water. And I'm going to draw out the molecules here. Okay, so this is our HCl, this is water, H2O, and then the products are chloride ion, Cl-, and this thing, which is called hydronium ion. And because it's a molecule with a charge, I'm going to put brackets around it so we can say that whole thing has this charge. All right, let's also write it in symbolic or in formula form. This would look like HCl plus H2O, and then the products are chloride and hydronium. Okay. So this is a chemical reaction. Two things, HCl reacting with H2O. All right, now let's see if we can make sense of this in the context of our definitions of acids and bases. So we would look at the left side of the equation and we could say, all right, which of these two molecules is the molecule that is giving up H+, and which one is accepting H+? And if the answer is neither, then it's not an acid-base reaction under this definition. There are more general acid-base definitions, but for our purposes, if there isn't a transfer of H+, if something else is going on, like one of the other chemical reactions you might have seen, that's not an acid-base reaction. It just doesn't apply here. But this is a reaction that transfers H+. And the way we can see that is if we kind of analyze what's going on across these structures, we can see that the HCl is losing its H to become Cl. So it was HCl, now it's just Cl. And then also, this is important too, it's changed charge. So this is neutral. HCl is a neutral molecule, but chloride is -1. So if you go from neutral to -1, that means that you have lost something positive or gained something negative. And so in this case, it's lost something positive. It's lost H+. And that's maybe the hardest thing for a lot of people that I found in understanding these reactions, is recognizing that the thing that's being transferred, that's being gained or lost, is charged. So wherever the H+ is lost from is not only going to lose the H atom, but it's also going to change its charge. It's losing a +1. So if it was neutral and you lose +1, that's like -1, so you end up at -1. If this was +2 on the left side and it lost H+, then it would become +1. So you're always going down 1 if you're losing a plus. And then on the other side, the water, the H2O, is gaining that H+. So not only is it gaining the H to go from H2O to H3O, but it's also gaining a charge. It's going from neutral to +1 because it's gained that plus charge. So both of those things are happening here. And that means that we can now label in this reaction going from left to right which molecule is the acid and which molecule is the base. So in this case, the HCl is the acid and the water is the base. All right. So if you've learned about some of this stuff before, this might be a little different than what you've seen in the past. For example, there's no mention of pH here, right? Water, H2O, we usually think of that as just neutral, but I'm telling you here it's a base. And that's because in this definition, this way that we define acids and bases is not intrinsic to the molecule. It's not like a property that this molecule always has. Water isn't always a base. This definition is telling us how this molecule is acting in this particular situation. Excuse me. So in this situation, water is acting as a base by accepting a hydrogen ion, an H+. And HCl is acting as an acid by giving up its hydrogen ion, its H+. So both of those things are happening, and we have an acid and a base. Another interesting thing about acid-base reactions is they can often be reversible. So instead of just thinking about the left to right reaction, we might also want to think about the right to left reaction, and we can make the same labels in the right to left reaction. So we can start on the right over here and say, okay, which molecule is giving up hydrogen to become something over here, and which molecule is accepting the hydrogen ion. And this way it's actually easier because only one molecule has any hydrogen. So that's got to be the one that's giving it up. Chloride can't give up hydrogen if it doesn't even have any. So this has to be our acid for the right to left version, and then this is our base. And so as you'll see, every acid-base reaction works this way. You transfer the hydrogen, and each side has an acid and a base. The other thing you might notice here is that in the process of going through this reaction, these acids and base kind of pair up. So the HCl was the acid, the Cl is the base. The H2O was the base, the H3O is the acid going the other way around. And that's actually something that a lot of people noticed. And so there's a word to describe that. And that word is conjugate. We say that HCl and chloride are conjugates of each other, conjugate acid or conjugate base. And then also the water and hydronium would be described as conjugates as well. All right, let's take a look at another reaction and see if we can do the same kind of analysis. So figure out which is the acid and which is the base in both directions, and then find the conjugate acid-base pairs. All right, so here's another reaction. We're going to use water again. And we're going to react that with ammonia and look at it going both ways. All right, so this molecule on the left is called ammonia, then we've got water. Then this ionized form, or this positive form, is called ammonium, the IUM at the end. And then we have a hydroxide ion here. Okay, so here's our new one. So if you are watching this later, go ahead and pause the video and see if you can do that same analysis. So see if you can find in each direction which is acting as an acid and which is acting as a base, and then find those conjugate pairs of each other. If you're watching live, I'll just pause for a minute or so you could do that, but if it wasn't enough time, that's okay. All right, so we're going to look at that same ideas that we just did. Looking from left to right, which is acting as an acid, which is donating its hydrogen, and which is acting as a base, which is accepting the hydrogen. So for this reaction, the ammonia is becoming ammonium, so that's accepting that hydrogen. So that's acting as a base. And water is what's giving up that hydrogen to become hydroxide. So that's our acid. Looking from right to left, we've got ammonium giving up its hydrogen. That's now the acid. And hydroxide accepting that hydrogen. So it's like giving it to the hydroxide. So that's the base. So notice here, the water is acting as an acid in this reaction, whereas we said it acted as a base in the previous. So that just emphasizes again that this acid-base definition is not something that is like a molecule is absolutely always an acid or a base. It's how it's acting in a particular situation. So lastly, we want to find the conjugates. Ammonia is going to be conjugate to ammonium. Other ways that we can say this, we can say that ammonium is the conjugate acid of ammonia. And we can also flip that around and say that ammonia is the conjugate base of ammonium. And then the water, the hydroxide are also conjugate. So let's take a look at these together, if we can see everything. Yeah. How does this work then if water and hydronium are conjugate, but then water and hydroxide are also conjugate? So we would say hydronium is the conjugate acid of water. Water is the conjugate acid of hydroxide. And then going backwards, hydroxide is the conjugate base of water. Water is the conjugate base of hydronium. So that would give us our conjugate pairs. The reason that we focus on this, or that we keep talking about these conjugate pairs, is this is how we can figure out fairly easily how to predict a reaction. So if we know that a molecule is going to undergo an acid-base reaction, and let's say it's going to form its conjugate base, so it's going to act as an acid and give up its hydrogen, then we can say, all right, well, what kind of a molecule is it going to form? It's going to form its conjugate base, and we can draw that. So let's list a couple starting molecules here. And then for each molecule, we're going to see if we can come up with a conjugate acid and a conjugate base. And to remind ourselves how this works, let's just put that right here, that when we make a conjugate acid, that means that we're adding hydrogen. So if the molecule, and I know this can be confusing, go back and replay it if you need to, but if the molecule is acting as a base, it's accepting that hydrogen to form a conjugate acid. So the conjugate acid has more hydrogen. If it's forming the conjugate base, it's losing hydrogen to do that. So the original molecule was the acid, and now it's losing hydrogen to form the conjugate base. So that's losing hydrogen. And then, as I said before, the thing that a lot of people mess up on this, adding or subtracting the H seems to be fairly easy. It's dealing with that charge. So we have to make sure that the overall charge of the molecule goes either plus or minus, depending on which thing we're trying to figure out. So let's do some examples together, and hopefully it will start to make sense. So we'll start with one that we've already looked at, water. The conjugate acid of water is what we get when we add hydrogen to it, hydrogen ions to it. So that's H3O, and then remember, we're adding a positive charge also. So that becomes H3O+. The conjugate base of water is when we lose that hydrogen, and that's hydroxide. And then we need to remember that that's -1 also. We're losing the hydrogen atom, but we're also losing that positive charge. So we're left with a negative charge since we started with a neutral molecule. We can also do this for a charged molecule. So we can look at, for example, hydroxide as our starting molecule, and we can say, what's the conjugate acid of hydroxide? Well, that means we're going to add H+. So if we add H to hydroxide, we get water. And because we're adding a plus to a species that's already -1, then that's going to be a neutral molecule. So no charge there. And then this is one we actually haven't seen yet. We can find the conjugate base of hydroxide as well by taking away another hydrogen. So we take away this hydrogen too. And then we end up with just O, and it's going to actually be 2-, because we lost that +1 charge. So we went from -1, we had to drop down to -2. All right, so hopefully that's making sense. Let's try a couple other ones that are not related to water. So let's look at bicarbonate, HCO3-. And then let's look at ammonia. And then finally, let's look at sorry, not that one. Let's look at nitrate, NO3-. All right. So again, if you're watching this later, go ahead and pause the video. See if you can work these out on your own. And then we can check with what I put in there. All right, so we're gonna do that same procedure. We're gonna add hydrogen, lose hydrogen, depending on which side we're on here. So adding hydrogen to bicarbonate is going to give us H2CO3, and we go from minus to neutral. Losing hydrogen is gonna give us carbonate, which is CO3 2-. All right, ammonia, we did this one earlier. If we add hydrogen to ammonia, we get NH4+. But what happens if we lose hydrogen from ammonia? We didn't do this. Then we get NH2, and it's got to be -1. If you're not understanding why these charges are changing, why these minuses and pluses are changing, go back again to that explanation earlier with the reactions and see if hearing that a couple times can help that make sense. Otherwise, let me know if you're still having trouble with it. All right, and then with nitrate, our conjugate acid is HNO3 nitric acid. And conjugate base, it's kind of a trick question here. There isn't a conjugate base. Why? Because there's no hydrogen in nitrate. So we can't have a conjugate base of something that has no hydrogen under this definition. We need to be able to lose hydrogen to make a conjugate base. All right, so that's conjugate acids and conjugate bases and how these things work generally in these types of reactions. Okay, so the next thing we want to look at is the other way of talking about, or another thing that we use in talking about acids and bases, which is pH and acidity. So where pH comes from, we're not going to go through all of the details of this. I think there's a good bit of it at the beginning of the acids and bases lab here as well with the calculation. So the pH is different from defining whether a molecule is acting as an acid or a base. A pH is saying how much hydrogen ion is in solution. So we're going from the kind of theoretical of what are these molecules doing in this situation to the very practical and specific of like, here's a solution of this thing. How acidic or basic is it? So the equation given in the lab is that the pH is the negative log of the hydrogen ion concentration in molarity. Another way of writing it that you'll see sometimes is hydronium instead. That's that molecule that we saw up here. And the reason that happens, so if we go all the way back to our first example here, when water, or when HCl, which is a gas, dissolves in water, it forms hydronium ions. And that's what gives that solution its acidic behavior. So all the things that we think about when we think about acidity, whether it's food and like sourness or just the reactivity, the way acids react, all comes from having this source of hydronium in solution, this molecule that can give off its hydrogens and become water. So by measuring the amount of hydronium in solution, we can get a sense of how acidic that solution is. Now, the way the pH scale works is it goes from about 0 at the most acidic. It can go a little negative too, to 14 at the most basic, and then 7 in the middle we usually say is neutral. So how do these numbers have to do with these, why is there this complicated calculation with logs and all of that? Well, where that all comes from is that it turns out that these concentrations of hydronium when you dissolve acids in water are fairly small. Small enough that they're generally measured in scientific notation. So something like 10 to the minus 3 or something like that, 10 to the minus 4, 10 to the minus 5, on the order of that range. So it makes more sense to measure that on a logarithmic scale. But in the same way, acids and measuring acidity or basicity of a solution is something that everybody needs to be able to do regardless of their math or science training. Like you need to measure pH sometimes if you're taking care of a pool or soil or whatever, lakes, whatever, other things like that. So it's got to be a little bit simpler than like dealing with big scientific notation numbers. So when you take a log of a number, what you're doing is returning the exponent. So the log of 10 to the minus 3 is minus 3. The log of 10 to the minus 6 is minus 6. And then when you put that negative on the front, you're flipping that sign. So if the hydronium concentration is 10 to the minus 6 molar in a given solution, then the pH is going to come out as just 6. And so that's a nice even number on the scale. But that also explains why the scale is a little bit backwards. In other words, lower numbers represent higher hydronium concentrations. Because what we're really saying with those lower numbers is 10 to the negative lower digit, which is actually a bigger number. So 10 to the minus 1 is bigger than 10 to the minus 3. And so a pH of 1 has a greater hydronium concentration than a pH of 3, and that's why the lower end of the pH scale is more acidic and the higher end is more basic. Right. Another thing to note about acids and bases is that both ends of this scale represent solutions that can be extremely reactive and dangerous. We often think of acid as being like really dangerous, or like in cartoons when the acid burns through the floor and stuff like that. But really strong bases can have the same types of effect. They can be corrosive, they can be reactive, to say nothing of potential poisons or other effects that these things can have. So you have to watch out for bases just like with acids. Along with that, I want to define a couple terms here that are often confused. That is strong versus weak when we're talking about acids and bases. When we say a strong acid, so when we say HCl, hydrochloric acid, is a strong acid, there's actually a very specific thing that means. And it's not related necessarily to the danger or the corrosiveness of that particular acid. Strong acids dissociate fully when dissolved in water, and weak acids do not. So what does that mean, dissociate? We're talking about this, again, this reaction way up at the beginning here. So when you put HCl, which is a strong acid, in water, it pretty much all goes to the right. It all goes to the right. So you're not really going back and forth here. You're not having really HCl whole molecules left in solution. When you put HCl in water, all that HCl splits apart. That's what that dissociate means, splitting apart. And instead it becomes Cl minus and hydronium. So the word strong actually comes from a strong electrolyte, which means lots of ions in solution. So strong acids do produce more hydronium ions in solution, but it does not correlate to their danger necessarily or the safety issues. So that's the thing that people get wrong. Weak acids can actually be extremely dangerous. For example, HF, hydrofluoric acid, is a weak acid because it doesn't dissociate fully in solution. It still stays together mostly as HF. But because of the fluorine there and other stuff that's going on, it is a really dangerous acid. It can eat through glass. It can eat through stone. That's the kind of acid that can eat through the floor, and you have to keep it in plastic or stainless steel because it'll eat through glass. Acetic acid, which is vinegar, can also be extremely corrosive and dangerous in its concentrated form. Acetic acid vapors can really damage your lungs. So we always have to look up, I don't even think dangerousness is a word, danger. Let me fix that, sorry. So, you can't just be like, oh, this thing is a weak acid, so I don't have to worry about it. Those are separate concepts. If you're actually going to physically be working with something that's an acid or a base, just like any other chemical, even if it's not an acid or a base, you need to look up the safety data sheets and figure out what you're working with so that you don't hurt yourself and you can use the appropriate protective equipment and controls and whatever else you need. All right. So you'll be doing, I didn't talk too much more about pH because you'll be doing it in your lab. You'll be measuring pH of things with pH paper and indicator solutions and that kind of thing. The thing that's really new is just finding conjugate acids and conjugate bases by looking at the formulas and then adding or removing H+. All right. Well, it looks like there aren't any questions right now. So I will say good night and let me know if anything else comes up. Otherwise, hopefully you'll be able to work through the module all right. And just after this week, we start our final module next Monday. So have a good night, everybody. And I'll talk to you again soon.